All right, so we're back into this now. We have a given sequence, the associated series, and then from that series, we create the sequence of partial sums. Why this is important, we haven't mentioned yet, but we'll just put that on the back burner for a moment. We also have this sequence from which we generate this series, from which we generate this sequence of partial sums. And remember, earlier in the previous video, we discussed this sequence converges. All right. Here's why the partial sums are so important. It's because of this statement. We are going to generate various and very specific kinds of series. And the important piece of information about that series is not what is the sum. The important question is there a sum? Is the sum of the series finite? That is to say, the important question is, does the series converge? Does the series converge? That really, for a series, is the ultimate question. Does the series converge? Not necessarily what actually is the sum. The question is there a sum? Does the sum exist? If the answer to that question is yes, then you can use that series to do other things. For us, our question, our focus, our entire goal is this sum finite? Is this sum finite? That's the question. Whether or not a sequence converges for our purposes is of lesser importance. Whether or not the partial sums exist, if you can figure this, the value for the partial sum, the formula, the behavior of the partial sums, for our purposes isn't the main issue. For our purposes, all we need, really what we're going to be focusing on is, does the series converge? And here's the rule. Here's why we bothered with these stupid partial sums. The sequence of partial sums. Here's why that's important. A series converges. Remember, that means is finite. If and only if I'll write this over here. The series converges if and only if the sequence of partial sums converges. And that is to say, limit exists. It is in principle, it's possible for this sequence to converge, but this series might diverge. These don't always have the same behavior. In point of fact, this sequence does converge because not only do these points approach a horizontal asymptote, these points actually are on the horizontal asymptote of 2. This sequence does converge, but this series does not. This series is clearly infinite. If you add together an infinite number of 2's, that is an infinite value. This goes off to infinity. And so in this particular case, this sequence does converge, this series does not. Over here, it turns out, we can see this sequence does converge. If you do the limit, you get a finite value. This sequence does converge. And this series does converge. So in this particular case, these two exhibit the same behavior. These two do not exhibit the same behavior. So remember, our goal is to find out the behavior of this middle guy. We want to know their behavior, and their behavior is not uniquely tied to the original sequence behavior. However, this statement, which we'll accept without proof, this is a problem for an advanced calculus course to prove. This statement says this: these don't always behave the same, but these do. A series converges if and only if its sequence of partial sums converges. This series converges if and only if this sequence of partial sums converges. Once you determine the behavior of the sequence of partial sums, that means you get the behavior of the series for free because they always are in agreement. If this sequence diverges, then so does this. And if this sequence converges, then so does this. Investigate the behavior of the sequence of partial sums, and you get the same result for the individual series itself. That is not what happens with these two levels. This top level and the bottom level, they don't always agree. This top level and the middle level, they do not always agree. This middle level and this bottom level, they do always agree. And so, our question then is this. Does the series AN, does that series converge? Well, there are going to be other ways. We're going to find some other pieces of information. But at this level, this is the only tool in our chest. Open up the toolkit and take this little rule out. The question is, does the series converge? So what do you have to do? You have to check out the sequence of partial sums. So, does that converge? Because these two questions always have the same answer. World without end, amen. These two questions always have the same answer. So, but this is easy to find. This is easy. What is this is a sequence, right? This is a sequence of partial sums. Does the limit as n goes to infinity of 2 times n? Well, that's 2 times infinity. And in our infinity arithmetic, that's infinity. That is not a finite value. Therefore, this sequence diverges. Therefore, this series diverges. The end. To determine the behavior of a series, you determine the behavior of the sequence of partial sums. That's what this rule says. Let's check this other piece. This is a little more elaborate. There's a little bit more going on. So in this case, does the series 1 over 2 to the n converge? Well, the series converges if and only if the sequence of partial sums converges. But we already showed on a previous video, this is one of the examples we worked out previously. This actually does converge. If you take the limit 2 to the n minus 1 over 2 to the n. Remember, everything gets divided by 2 to the n. 2 divided by 2 to the n, divided by 2 to the n. And we found this actually worked out to 1. And so, does the sequence converge? So we say, therefore, Sn, I'll write it down here. Therefore, Sn converges. Therefore, the sum, n goes from 1 to infinity, of 1 over 2 to the n, converges. Not only that, not only do we know this sum is finite, we actually know what the sum is. If this limit works out to be 1, then this sum works out to be 1. This limit works out to be 1, therefore this sum. So if the sequence of partial sums has limit equal to 1, that guarantees that the series, the original series, has sum equal to 1. So in this particular case, what we can say is that this original series that sum is 1. Not approximately, it is precisely 1. That assumes you've taken all the terms. If you chop off, if you only take the first 100 million terms, it's not equal to 1 anymore. You need to take all the terms, and that sum is equal to 1. That's the definition of this sum. That if the sequence of partial sums converges, then the value of the series is the limit value of that convergence.